So let's get started. We're going to actually talk about planning clocking domains for Dante, Q-LAN and AES67. We're going to talk about these really in terms of Q-SYS. I give the disclaimer whenever I do this webinar that I am not a network engineer, and I am not a network engineer. I'm just an AV engineer working for QSC. So the only thing that I want to do at the beginning of this is we're going to take about 5 minutes and just talk about some definitions. And then we're going to get into a whole bunch of examples that are going to sort of build up the different things that we can do within the Q-SYS environment. And I actually have Q-SYS Designer open, so we can share that at some point here as we go along. So let's get started. So the first thing we really want to talk about is really what is network time protocol, what is precision time protocol. And that's not on this slide yet. This is a little bit of prep work with some definitions so that we can get into our slides. So you're going to look at the same slide for a few minutes, but bear with me. Network time protocol, NTP, synchronizes the clocks of computers in a network. Usually synchronizes it to something like the atomic clock or some other clock device. There's lots of companies out there that have NTP servers, and you can always subscribe to those NTP servers. And all we're doing is getting everybody to sort of get to the same time. But unfortunately, the accuracy of NTP is within terms of milliseconds. Sometimes over the internet, tens of milliseconds. So you may be off by a half a second. You may be off by a second. You may be off by some small chunk. So we came up with, not we, but the great powers that be in the networking world came up with precision time protocol. Precision time protocol is defined in the IEEE 1588 standard. You can actually see PTP version 1 is the 2002 and PTP version 2 is the 2008. I would bet at some point we're going to have a PTP version 3, but I haven't seen a whole lot of documentation on that yet. But precision time protocol gets us to the sub-microsecond or nanosecond precision level of time so that we can actually sync up audio streams. We can sync up things that are more time critical than just the clock at the bottom of our computer. So according to the latest IEEE 1588 standard, we have some terms that we need to talk about. A lot of times you'll hear grandmaster clock or clock master, clock slave, clock follower. I'm probably going to use a lot of those interchangeably. I try not to use words that are offensive, but unfortunately, I've been dealing with PTP since 2002, like everybody else. So I apologize if I say a wrong word here. But in the new standard, they actually have a term for the grandmaster clock as time transmitter. So that's the word time transmitter. And then the sort of clock followers are called time receivers. I tend to use clock leader and clock follower, and we'll try and stick with that throughout here, so we can all agree on that terminology. So getting into actual PTP, it requires multicast on your network. So the PTP traffic is multicast traffic. There are currently, like I just said, 2 versions, PTP v1, PTP v2. PTP v2 is not backwards compatible. These are 2 separate and independent things that have had to learn to get along together. The PTP data is extremely sensitive to jitter on your network. Why? Because it's really, really small packets, but a lot of them. So think about 100 bytes a packet, but about 100 packets a second, sometimes more than that. We have lots of different types of PTP devices on our network. I'm going to run down some of them. We're not going to do a really deep dive on that, but you can always Google some of those things. But there are different clock types. You have your grandmaster clock, an ordinary clock, and a boundary clock. We're going to talk about all 3 of those. And then you have a role, as in it is the time transmitter or the time receiver, leader or follower. The grandmaster clock is your primary source of time in PTP. It's responsible for the root timing reference for your sync message. If we're now actually looking at the slide, that initial sync message is always coming from your grandmaster clock. Quite often it's connected to an external time source, such as a GPS satellite or an atomic clock or some other device that actually syncs us to the world clock at the same time. All other clocks are going to sync directly or indirectly with your grandmaster clock. An ordinary clock runs PTP on one interface. It can actually be a role as a leader or a follower, but it's usually an end point device that requires its time to be synchronized. Boundary clock runs PTP on two or more interfaces or IP addresses. It can sync one network segment with another. So it can actually sync PTP v1 and PTP v2 together. Keep in mind, again, PTP v2 is not backwards compatible. So some device has to be that bridge, and that's what we call a boundary clock. It has an upstream interface that connects to the grandmaster clock, and it follows the grandmaster clock, but it can actually connect to downstream devices and can serve them as a clock leader. When we get into PTP v2, we add another clock type to those three clock types, which is transparent. And that's made up of end-to-end or peer-to-peer clock communication and clock data, which I am not going to dive into, but you can go in and look at it. It sort of is, it adds the ability for devices to forward clock information, which really helps keep things in sync. It also allows the devices that are forwarding clock information to actually keep track of the amount of time it takes them to forward clock information. Peer-to-peer clock messages in PTP v2 actually allow the device that is using peer-to-peer to actually query upstream and downstream to find out what the delays are between all the messages and allow them to sync a little bit better. So really, when we're talking about PTP, we're talking about that initial sync message from your grandmaster clock, your clock leader, and it gives a time, and then you get a response. And again, the response is multicast. All this traffic is multicast traffic. And as these messages go back and forth, they use the timing of those messages to sort of sync themselves together. In PTP, there are different message types. You have event types and general types. Event types are all of your time critical messages, anything that's time stamped. So a sync, a follow-up, a response, a delay response. And then you have general messages, which are announcement messages, talking about quality of the clock, the best master clock algorithm, which we're going to talk about further down the road, uses it for elections. And basically you have general messages that are not time sensitive. All right, so all of that gives you sort of a base amount of information for PTP, both V1 and V2. It's not really, we don't have a slide for it yet, but I always like to give those basic information because now we're going to start talking about how it applies to Q-SYS and how it applies inside Q-SYS Designer. To do that, we're going to go through some scenarios. The scenarios are going to feel really basic, but we're using this to sort of give you okay, here's what we're going to do next. Here's how you're going to do this next, and layer on more information as we sort of build through it. So bear with me as we go through this. Our first scenario are two cores. I told you this was basic. You have two Core 110s on your network, but they don't have any peripherals. There's no network audio devices. There's no anything. They're just both sharing network space. They might be running a simple file like what you see here, but you can see we don't have any streaming Dante. We don't have any peripherals. We don't have any other devices. So in this scenario, the core, Q-SYS core, will not use a PTP clock if it's not needed. What used to be, we always did PTP, but if we don't actually need the clock, we won't use the clock. We won't actually get a clock in there. We won't actually turn on a clock. So 2 cores that are running standalone systems and they don't need a clock, they're not even going to use it. They're not going to start sending out messages. They're not going to try to sync to anything. Really is our simplest basic configuration. To look at that in Q-SYS Designer, if we look at design properties, you can see this PTP force on. You can actually, and I'm just going to let that hover. Hopefully you guys can see the pop-up there. Used to enable PTP on an interface when it would not otherwise be required. So if you do want PTP in this basic scenario, you can have it. You can change this to LAN A, LAN B, either interface or both. Or you can actually leave it off and let your cores just sort of do their thing. So now we're going to add some complexity. We've gotten through the simplest of all the scenarios, but I think the reason we talk about that first scenario is the important thing to understand is that if a clock isn't needed, the core isn't going to attempt to start sending out timing or PTP messages when it doesn't have to. So scenario 2. Q-LAN peripherals. We have in our system, we still have our 2 Core 110s still on the same network with each other. And we now have an IO8 flex per core. So now we have a clock. We need a clock. We have Q-LAN devices. Q-LAN is Q-LAN and AES67. We talk about them a lot together. And that's because our audio streams are essentially AES67 streams with our Q-LAN wrapper around it. So we're using a lot of those same protocols. So let's get into this. If you have these 4 devices and you just throw them on the network, how do we elect a clock leader? How do we figure out who's going to be the grandmaster clock in this situation? When all other things match, when all of the different algorithm components match, the lowest MAC address is going to win the clock election. Okay, so that's why we're looking at this scenario so that you can understand those 2 cores are identical. They're probably even running identical files. They have probably the same default values out of the box. And if you just take them out of the box and plug them into the network, they're going to pull an IP address or an APIPA address, some sort of an IP address so they can talk. And the one with the lowest MAC address is going to win the election. We're going to talk a little bit more about that, but we have some concerns now. Clock election has taken place, and we actually have a core that has won the clock election, but it may not be the core that we want. We need to actually understand some ways to sort of not force the issue, but define the issue when we're looking at a network. So that's what we're going to talk about next. So we have our same scenario, our same cores, our same 2 IO flexes, IO8 flexes, our same 2 obsolete IO8 flexes. It's one of my favorite boxes. So, and we need to talk about how we can control that and what the clock election is. I've talked about there's a clock election, but I haven't really defined what that is. So let's do that now. So we have BMCA, which is called the Best Master Clock Algorithm. It is the algorithm which the network uses to determine which clock becomes the grandmaster clock, which clock becomes our clock transmitter. So there's a whole bunch of stuff in there. We don't use all the values in there, but there are other devices that do. So this is a algorithm that runs top down. So priority 1 is the first thing it checks. So PTP priority 1 checks that first. Class checks that next. Accuracy next. Variance priority 2. UID. The UID, I'll talk about that first. That's the MAC address comparison. It's kind of like making a hash of the MAC address and comes up with an 8-byte number, and the lowest number wins. Every now and then, a MAC address that's slightly higher will get elected because of the fact that it is a hash of the MAC address, that it's not a direct comparison of the MAC address. But in general, the lowest number there wins. As we go through this best master clock algorithm, the lowest number always wins. Just keep that in mind, that like as we talk about the different values, the lower the number, the better every time. So PTP priority 1. It's a value from 0 to 255 that you manually configure. The lowest value wins, like I just said. And it is the first thing that gets compared. So if you're thinking about setting up a network that has a lot of cores on it and a lot of devices that may or may not be vying for Grandmaster Clock status or clock transmitter status, you can use PTP priority 1 because it is the first thing that gets compared in the clock algorithm in the BMCA. Class is the next thing that gets compared, and it tells what kind of source the clock has. The default value is 248, and for the most part, AV devices sit on 248. I don't see a lot of variance. The only thing I see when you get into variance is that things that are actually like a GPS satellite that actually is a clock, or something else that is linked directly to something that's a master clock out there in the world. A clock that is connected to GPS, the class value is 6. When it loses its GPS connection, it becomes 7, so it is dynamically changeable. But the default value for most AV devices is 248. Accuracy, how accurate the clock is to true time. There's a value there that sort of tells everybody else on the network how accurate are you. There's always some slight deviation, but obviously the lower the value, the better. The more accurate it is, how true it is a value that is compared. Variance is how stable the clock is. How much is it going to drift? The less it drifts, the better it is. Again, the lower the number, the better. PTP priority 2 is another user configurable value, also 0 to 255. Lowest value wins. So if everything else is the same, PTP priority 2 value can be addressed, and you can change that, and it will make a difference in which clock gets elected to the transmitter status or the Grandmaster clock status. And then that UID that we've already talked about. When this algorithm finishes, the Grandmaster clock is sending sync messages at regular intervals. When the algorithm finishes and a current clock master recognizes that there's a new Grandmaster clock out there, it stops sending its sync messages and the new clock takes over sending the sync messages. That little gap where there are no sync messages is where we hear audio cutting out, where we'll hear a break in the audio because all of a sudden everybody has to move to sync to the new sync message. Q-SYS defaults, PTP priority 1 is 254. PTP priority 2 is 100. Interesting note, all Q-LAN peripherals always have out of the box a PTP priority 1 value of 255. We do that so that at no point will the peripheral win a clock election over a core. Micah, what would be the use case to set PTP priority 1 and 2 to different values? We're actually going to answer that as we go along. So bear with me a little bit, and if I haven't answered that in the next 15 minutes or so, I'll come back and get you covered. So in our situation, back to our situation, where we have our 2 cores, what we did in core number 2 to make it the Grandmaster clock is we actually went in and changed the PTP priority 1 value. So where is that in Q-SYS Designer? It's in this, I'll just open this again. So you go here to File and Design Properties, and all you have to do is double click and type in a new value. So if we want to define out of those 2 core 110s, which one becomes the clock master, we actually can do that by changing that PTP value. If we change PTP priority 1 value on one of the cores and the other stays at the default of 254, lowest value wins. We've now said, okay, core 2 is in a rack. core 1 is in a little portable thing that may or may not get disconnected. We want core 2 to be the grandmaster clock for this situation. So we change that PTP priority 1 value. I am going to, a little quick side note about Micah's question. PTP priority 1 and PTP priority 2 values have nothing to do with each other. One is a number that gets addressed first. The other is a number. They are user defined. We tend not to play around with PTP priority 2 all that much because we actually want to force the clock election before it goes through all of the rest of the algorithm. Just an FYI. But you could, in some cases, if you wanted to, set PTP priority 1 the same, and then use PTP priority 2 to make some sort of a distinction on the network. So we're going to move on to our scenario 4. We're getting there. Scenario number 4. We have our same 2 cores. We have our same 2 IO8 flexes, right? But we want to not have them talk to each other at all. I'm going to actually read this question before I interrupt myself again. Is there any way to dynamically set the priority, perhaps with DHCP or radius, so that we can avoid having 2 different design files? There is not. Even Dante Domain Manager doesn't allow you to do it dynamically on the network. I'm sure there might be a networking way to do it, but as far as I know, there is actually not a way to make it a programmatic thing within Q-SYS Designer. All right, so we're going to talk about our scenario with the alternate domains. So say we have our 2 core 110s and we have our 2 IO8 flexes, but we just don't want them to talk to each other. We don't want them to exchange data. I don't want audio on core 1 to stop if I push audio or push a file to core 2. We want them to stay separate. And that's where we can actually change the PTP domain. And Michael, that might be a solution where you can actually have the same design file and in one of the 2 change the domain. But again, you're right. It does mean that the file is slightly different and it is 2 physical files, because when you're dealing with these settings, design properties, this tracks with your file. This tracks with your core. So when you push this in, it pushes those values to the core and it stays with the file. So Michael's making a pretty good point for everybody to be aware of. All right. So in this, we're actually going to change one of our 2 core 110s, back to our fun 110s. We're going to change one of our 2 core 110s to PTP v2 domain 1. So default PTP v2 domain is 0. All devices that are Dante devices are automatically domain 0 unless you go into Dante Domain Manager and actually change them, which you can do, but I'm not here to talk about Dante Domain Manager. I'm here to talk about Q-SYS. But if you take any of the Audinate classes or their Dante Domain Manager class, which is a fantastic class, you'll see some of that information and understand how you can make those changes. But by default, Dante devices are domain, all Dante devices are in domain 0 by default. But we don't have any Dante devices just yet in our scenario here. So we're going to actually just change one of the cores to domain 1. We can even leave it at a PTP priority 1 of 254 of the default. And you can actually run the 2 systems and they won't even see each other or talk to each other. So you then would have actually 2 grandmaster clocks, one for PTP v2 domain 0, one for domain 1. And that actually, the best way to put it is they just ignore each other's clock messages. There's 2 clock masters, one on each domain. So on the network, there's going to be 2 grandmaster clocks. But because they aren't on 2 separate domains, they essentially ignore each other. One note, if you have to share audio streams, you have to stay on the same domain. So the Flex IOs have to be in the same domain as the cores. So devices that share audio must stay in the same domain. There is one way around that, which we will get to later on, but we're gonna work with that for now. All right, we're plowing through our scenarios. This is good. This is where I always take way too long and everybody yells at me for going over. Scenario 5. So now we're going to add some peripheral devices, which in most systems, you have these peripheral devices. So we have UND6IOBT. It has an Ultimo X in it, so it is AES enabled, and we're gonna enable AES on it. And then we have the DX4i, which is that 4XLR input plate. It only has an Ultimo chip. It is just a Dante device. It is a straight up Dante device. No, don't pass go. Do not collect $200. It's never going to run AES67. So what do we do with these, and how do we handle it, and how do we get ourselves to the point where the clock grandmaster is what we want it to be? So first things first, if you have a device that is AES enabled that has the right chip in it, you can turn it on in Dante controller, and it basically turns on a PTP V2 clock in those Dante devices. So they now have a PTP V1 clock and a PTP V2 clock, which, as you configure, allows them to actually operate as a boundary clock. Devices with AES67 enabled still utilize PTP-V1 for synchronization with the other Dante devices on the network. We've already talked about Dante devices being in domain 0. And then we just are getting into now this concept of a boundary clock. So now we actually have a PTP-V2 PTP2 V2 sort of clocking scheme in our system, and we have a PTP-V1 because we have a device that's a Dante only device. So let's talk a little bit about how to handle that. If we just left it as it is, plugged everything in, got everything talking, the device that is our boundary clock will also most likely be elected our grandmaster clock. There are a lot of devices that actually, if they are the boundary clock, they start having problems if they're also not the grandmaster clock. And this is where you can actually see audio start doing really weird things in your system and on your network. So we want to control this. But in this system, in this scenario, if we just plug everything in, this is what we get. We will use the UND6IO to sync to our PTP-V1 domain 0 device, and we will use the UND6IO to sync back to all of our Q-LAN devices. It is our boundary clock, and that's essentially what our boundary clock is going to do. In this case, it will most likely also be elected our grandmaster clock. I do want to say that everybody thinks that these are things that like this scenario is hinky or not great. This will work. I've seen systems run like this. As long as the device that's the boundary clock and the clock leader is stable and not going to fail every 5 minutes. Wow, Michael, you're asking all the good questions. We're going to get to that. But as long as the device is stable, this could run for 20 years and have no problems. However, when I set up systems and when I do larger systems, I try to take a few minutes and think about this and decide where I want the grandmaster clock leader to be. And that's really kind of what we're going to do next. So scenario 7, yes, I skipped one, but the one I skipped, you don't need to worry about. This is where we actually get into sort of answering the next 2 scenarios. We're going to answer Michael's question. So his question is, if the cores have a Dante license, why isn't the core the grandmaster for both PTP V1 and V2? It is. It can be. But we have to ensure that it is. We have to be deliberate about making sure that it is. And that's what these next 2 scenarios are really going to talk about, is how we take those couple of steps and use the settings in Q-SYS Designer to do that. So we've got our system, and right now we've just plugged everything in, and our UND6IO-BT is our clock leader, and we want to do something about that. So first thing we can do is we can make sure that the core ends up being our boundary clock. To do that, we can actually add software-based Dante to the core. Even just dragging the block into your design file, if you're not using it, will actually say to the core, hey, you need a PTP-V1 clock. And now our core has both V2 and V1, and it can then act as the boundary clock. It will most likely try to be the boundary clock in this scenario. In the scenario that we're looking at with the gear that we're looking at, as soon as we drag this software Dante into the file, it will, the core will do everything it can to become the boundary clock. So basically, you can do that. PTP domain only applies to PTP v2 devices. So if we drag Dante, a Dante software Dante in, keep in mind, it is still at domain 0. The core will act as the boundary clock. But one thing the core won't do is it will not do separate clocking between PTP-v1 and PTP-v2. The reason that the Core 510 was such a popular box and why so many people had it is you could put a Dante card in it, and that Dante card in it would actually be reclocked, so that you could actually have a separate PTP-v1 clock and a separate PTP-v2 clock. So if we go ahead and make the Q-SYS core, we're just going to use core 1, our boundary clock, by adding that software Dante in, we're getting closer to what we want to get to. We're getting closer to Michael's answer. And we have that, the core is our boundary clock, but the UND6IO is still winning the clock election because of the MAC address. So our next step is to go back and do exactly what we've been doing in the other scenarios, where we're going to change the PTP priority 1 value of our core 110. So that core 1 now has PTP-v1 and PTP-v2. It's our boundary clock. And now by changing the PTP priority 1, we're turning it into our grandmaster clock and our boundary clock. So this is our ultimate scenario. And this is where we want to do this. And I know that these scenarios I've been through are really kind of simple scenarios, right? But the idea is that we want to build the muscle memory and thought process to be very deliberate about these decisions. You could be in a system or in a room with, or in a building with 30 cores all sitting on a flat network. In fact, I'm going to a job site later on this week where that's exactly the case. And we have to sort out who's going to be the clock leader. Because right now, this core 1 is our boundary clock. This core 1 is our grandmaster clock leader. But if I have to push a file to core 1, it's going to turn off the audio in core 2 for a couple of seconds while clock elections take place. So how do I manage that? How do you manage that on big networks? I think that the idea here with this webinar is to get everybody to sort of think about that and be more deliberate about it. We're not done yet, so we're going to talk about some of those real world scenarios. Meeting room. This is your typical meeting room, although maybe not an amp that big, but I love that we went and found like an older amp picture. But you have say a Sennheiser TCC2 in the ceiling. You've got some kind of a small core. You've got an amp. I know that they threw this particular CHQ amp in there because it's a Q-LAN device. But let's just assume it's a little SPA Q amp. You have, say, a video encoder, video decoder, pretty typical small conference room configuration, right? So when you look at this configuration and you throw it all together and connect it all on a network switch, as we've all seen, the Sennheiser mics, the Shure mics, they want to be the grandmaster clock. They want to be the preferred clock master. Some of them, in some of the earliest versions of the Shure MXA 910 and like early versions of the firmware on the 920, that preferred master was actually checked out of the box on some of them. So you just have to be aware when you do this situation, the microphone might become your clock master. In this scenario, it's probably fine, right? It's probably no problem at all. You could run this. But what if you're in a situation where you have 5 of those rooms and they're all on the same network? And now you want to take a minute and think thoughtfully about where your grandmaster clock is. I'm going to talk about this scenario for a couple of seconds longer because I'm actually, the building that I'm going to is this exact scenario. I have 15 rooms that are all identical, and they're all running a core, an amp, some encoders and decoders, ceiling mics, and Which one do I make the clock master? Which one do I make my grandmaster clock leader? Which one? I can tell you in the situation that I'm going to, that we're actually going to put a Core Nano in an IDF and make it our grandmaster clock. That way, I can push a file to any one of these rooms, and I don't take down any other room. But if I wasn't thinking about it, wasn't being deliberate about it, something is going to win that clock election, and whatever wins that clock election can adversely impact every other room in your building. You need to really take the time to think about these things. Take a second here, and I'm going to answer some questions. Are the cores Dante cards virtual? Yes, there are no actual Dante cards. It is software Dante. The only place where we have a physical Dante card are in our I/O frames in our Core 510i, which has an actual Dante card, which is a real card and allows you to get the reclocking if you wanted to separate your clocks. William says, if the core is set up as a boundary clock, will it sync to an external GPS PTP V2 clock? Yes. I've actually seen that in action. There's a end user that we have that does exactly that, where every one of their buildings, they put a GPS satellite, and they actually sync all their cores to that, and the core is still acting as a boundary clock. It's acting as a boundary clock because there are Dante devices on the network. What about using a GPS master clock like a Brainstorm DXD16? Yeah, those are all fine. And there are a lot of things in our help file about how to actually connect to those. You use our GPIO to connect a GPS master clock into a core or into a centralized core, and then you can use that as your grandmaster clock. Those are all very, very valid options, especially in buildings and spaces that are production based. If you're doing streaming video and audio out to the outside world, you almost always are going to need a standalone GPS master clock. All right, back into this. A couple more scenarios we've got here. So in this scenario, we can actually modify PTP, the PTP1 priority and force that room B to be our master clock. But in a real world scenario, you might think about putting something else that's going to end up being your grandmaster clock. Because right now, if I push a file to room B, the core is going to go offline for a hot second. A clock election is going to happen. Something else is going to become the master. And then when room B comes back online, it's going to continue to be the master. So you really do need to be deliberate about this. We get so many calls into our support where audio is cutting out, where the clock election keeps happening over and over again because things are not set properly in our cores, on the network, etc. All right, so let's take a look at another system. So we have a paging system. Everybody loves paging with redundant 5200s. One thing to talk about, the reason we talk about redundant cores here for just a minute is you want to look at the MAC addresses of your redundant cores and actually think about which one becomes the primary core. Remember, the lowest MAC address wins. So you may actually want your primary core of your two redundant cores to be the one with the lower MAC address, and then have your secondary be a slightly higher MAC address. So that, again, if core 1 fails, we want core 2 to take over. But if core 1 is online, we don't want core 2, that's our secondary, that's our backup core, to be the grandmaster clock in this scenario. So that's actually why we bring up this. Now let's take our paging system and assume we're going to add some stuff to it. Again, I'm going to use the same little Bluetooth plate. Say, we're in a casino and they add a Bluetooth plate to the little store that's selling chips and stuff by the front desk. And all of a sudden, adding that, it will win the clock election. It will become our boundary clock. But if we've actually set up our redundant 5200s properly, we can actually get it so that it's a non-issue, non-starter, not a problem. If we've set our PTP priority 1, we know that we want our core to be the Grandmaster clock. And then if we actually take our 5200 and we put Software Dante in there, we actually turn the core into the boundary clock as well. One thing to note about redundant cores as well, they share the same PTP configuration because they share the same file. Remember, those PTP settings go with your designer file. PTP priority and domain settings are shared between those cores. So one goes down, the other takes over. They should both essentially make sure that you stay with those two cores as your Grandmaster clock. So then we're going to talk about this situation. And the reason that this campus building is even in here as an example is it gives you a good sort of a heads up on how to mix and match Dante, or not Dante, PTP domains and PTP priority 1 and changing some of those values, which sort of, again, answers one of the questions that we've had so far. So we have 3 classrooms that have a core and an amp in them. We have a building PA system with some background music, and we have an auditorium, and there's this little remote box. The Axon boxes aren't made anymore. I really wish we'd put something in, but we have a remote box that's an IO box, and that box is a Dante device. So we have this whole situation where if these are all on the same network, the Axon device may end up being our boundary clock, and it may end up being our clock leader. There's some things we can do to help out, though. Do the classrooms need to share anything with the auditorium? Does the building PA need to share with the auditorium? Could we separate the auditorium off? Could we separate all these other rooms off? And I think this is about making your system stable and resilient, right? So if we actually take this configuration and we take classroom 1, classroom 2, classroom 3, and we put them all on PTP domains that are not 0 because we don't have any Dante devices. Same with our building PA system. And then we take our auditorium, we leave it on domain 0, but now it's separated off. Now every room is its own Grandmaster clock. And again, in a situation where you have to push a file or make a change or update things, this is where you're really getting into a system that's going to be robust. It's getting you to the point where your stability is where you want it to be. And then just one other thing, and then I'll answer the last couple of questions. One other thing with this that's really interesting is you can actually in Dante or in Q-SYS use what we call our WAN streaming IO or WAN streamer. God, I can't even say that well. To send audio between the rooms, so you could still share audio if you wanted to, but it's not going to be clocked or synced. My brain always calls it free run audio. That's probably an incorrect term, but essentially you can do that. So you can say, hey, I'm going to send an audio stream from the auditorium to the classroom. I don't care if it's lined up with any clock master at all. I just need that overflow to work. It doesn't need to be synced up exactly because the person who's in the auditorium is not in the classroom. The person in the classroom is not in the auditorium. So you can actually still make this a cohesive system while managing your clock and your clock leaders, your clock followers, and your boundary clocks. All right, so I think that's actually it. The recap, you guys can read the slide. I'm going to answer some questions. Can you elaborate on the difference between boundary clock and ordinary clock? Why would a boundary clock be necessary? So an ordinary clock only talks on one interface. So it can only talk to one other device. A boundary clock can talk on 2 interfaces, so it can talk to 2 devices. A boundary clock is really necessary when you have things that are in PTP v1 and PTP v2 because the 2 are not compatible. So you have to allow for some way for time-sensitive messages to be synced properly on the network, and that's where that boundary clock is. And that difference between boundary clock and ordinary clock is really the number of interfaces it can communicate on. If you log into a large system, is there a place you can check to see what device is the master clock, or do you have to go through and look at each device? There's some tools, Jason. One of the tools that we use a lot is called PTP Track Count. And PTP Track Count, you can go and get it. It's free software, and it actually allows you to see all your IEEE 1588 traffic on your network. You can actually see the clock election happening. You can unplug and plug in devices and just watch it go crazy. And this is a really good tool. There's a couple of other tools. This is the one I kind of like the most and have used the most for sure. And that means that you can actually sort of see what's going on and where that's going. You can also look in Dante Controller. Dante Controller, if you're using PTPv1, will show you at least that side of what your clock master is and what is your follower and where things sort of fall in the hierarchy. All right, next question. In a scenario with a portable Dante device and a core with PTP set for it to be the clock master, say a Netgear 4250 switch with video Dante audio profile, is there a PTP setting that would cause Dante subscriptions to show correctly in Dante controller and compromised in a designer file? I don't know that would, the subscription in the designer file doesn't have a lot to do with PTP settings. However, I have actually seen that happen, what you're talking about happen when your sample rates don't match. I'll give an example of that. I had that exact scenario. I go into Dante Controller, everything is matched up perfectly fine. I go into the designer file and it's showing that compromised. 99% of the time when I see that happening, I actually see that being a sample rate issue. In my case, I actually had a device that had reset its sample rate to 96. So it was compromised, but it was Dante Controller, it doesn't really care. So it was showing that the hooks were all there. I just had to fix the other issue. So I would say that that's one of those where you might want to look for another underlaying issue. Justin, is it best practice to have the core always be the boundary and master clock? I mean, I want to say yes because I'm a Q-SYS employee, but you might have situations where you have a GPS clock that's going to be your grandmaster clock, where you have other devices that may serve better for that. One thing that we do find a lot, though, is a device that is the boundary clock and is not the grandmaster clock leader. A lot of times with peripheral devices, especially like the little wall plates and all those little throwdown boxes that we all use, if it's the boundary clock, it likes to be the grandmaster clock. That's a big deal with some of these smaller devices, especially on the Dante side, on the PTPv1 side. PTPv2 is a whole lot more stable when it comes to that. So you can have a separate boundary clock and master clock. But you know, like my thing that I tell people is start out with being deliberate about it. Start out with having them be the same, and then see what happens with your network traffic and use some of those tools that I've just shared out with everybody. Whew. Feel like I've been talking for an hour. Oh, wait, I have. All right. Kelly likes to write a lot. I'm going to read it out loud, Kelly. Let's do this. In a scenario with a portable Dante device, oh no, you've already done that. There's a PTP setting.
Clear out the ones that I know you've.
Oh, is that what you're doing? Dan is back, everybody. I didn't see him come back.
Oh, that's okay. One thing on Jason's question about, is there a place where you can see who's the master clock? You can go to the status block of the core if you drug that into the design, and it'll show you what that core is, who the grandmaster is. But anyways, no big deal there.
Yeah, that's a great point. I'm glad you brought it up, because Core Manager, if you go into Core Manager, you can also see if the core has been elected to be the clock leader. You can see that in Core Manager as well. Cool. Hopefully we don't have, I answered all the questions, Dan, but I didn't clear them out of the queue.
Okay, no problem. I think until we answer them live, I don't think they show up yet. They're only we see them until they're that way. That's nice though. Either way.
Yeah. Cool. I think that covers everything. I'll just give that sort of recap. My recap is the tale of woe is take the time to plan it. If you're a field engineer and you're going out and you're commissioning something, take time to think about this. Don't wait for, don't wait for the users to start having issues or audio to start cutting in and out. Be deliberate about it as you go about your design. Think about your devices as well. Every device out there may have a different default PTP priority 1 value. I think I'll give Shure as an example. Shure MXA 920s. I think it's 128. So be really deliberate and don't be afraid to ask those questions and get that information. The bigger your system, the bigger your network, the more devices are talking to each other, the more you're going to need to take the time and really pay attention to what you're doing with your domains and with your clocking and with basically with how your clock master is elected as well. So hopefully this has helped everybody out a whole bunch. And thank you for joining me.
Yeah, thanks everyone. We appreciate the investment of time. And like I said at the beginning, for those of you that weren't on yet, because we did have about 15 people join, you will get a recording of this and a PDF version of the presentation. So yeah, thank you very much. Later. Is that a thank you in there? Just so I'm clear, now that we have flex devices and peripherals, we need a clocking mechanism, correct?
You do. Our peripherals, I think I said this at the beginning, our peripherals are set to 255 as a PTP priority 1 value. So if it's just Q-LAN devices and our QIO boxes, they will automatically sort themselves, and our core will be the clock master.
All right. Well, if we've got no other questions, we're gonna call it a webinar. Howdy. Oh, hey, Scott Carlock, good to see you. Hopefully you learned something. So, all right. Well, great. Thank you all very much. Have a great day. Thank you, Angela.
No problem. Thanks, everybody.